Hopefully you've watched through the lecture video that corresponds to section 2. So I'm going to continue to work through some examples out of section 2. So the first couple of problems deal with the definition of a limit, the formal definition of how we get a limit. So this one, they ask us, first of all, to find the limit of this function 5x plus 9 as x approaches 9. So if our function is a polynomial, then it turns out that we can find the limit of that function by direct substitution. If we can directly substitute our value in and it's not undefined or indeterminate, then our limit is our answer. So 5 times 9 is 45, plus 9 is 54. So the limit here is 54. So then they ask us, after we get that limit, to find the largest delta that's greater than 0 such that this is true and this is true. So let's remember what this notation means. So this notation means the distance between a given y value and the limit. So if we look at some graph, some function, and since our function is linear, we'll just, sorry, that's a little thick. Draw a straight line. So we're looking for the limit as x approaches 9. So let's just pretend that 9 is here. So this is the point we're approaching. So if we pick a point a little bit to the right, that point has a particular x value and it has an f of x or a y value. So f of x minus L, that's the difference from the y value to the limit. The limit is the y value that we're approaching as our x gets closer and closer to an x value of 9. So this is saying that as the distance between an arbitrary point and this point, as that distance gets closer and closer to 0.1, or if that distance is less than 0.01, then how does that correspond to a distance in the x direction? This means a distance in the x direction. So c is the x value we're approaching. This x is just the x of an arbitrary point. So if in the y direction we're within 0.01, so if that distance is less than 0.01, then what is this distance less than? So if we're so close here, how close are we here? So that's what that notation means. So how do we figure this out? So f of x we're going to replace with our function, 5x plus 9. L we're going to replace with the limit, which is 54. So the distance between our function, an arbitrary point on our function, and the limit is less than 0.01 whenever the distance between the corresponding x and the 9 that we're approaching is less than delta. So we're looking for delta. So how do we do this? Well, what we need to do is we need to simplify this absolute value. We get 5x 9 minus 54, that's negative 45. We can factor a 5 out. And it turns out with absolute values that if we have a product on the inside, we can take the absolute value of each piece. We can take the absolute value of 5 times the absolute value of x minus 9. Now, things that are added and subtracted, that doesn't work with, but with a product and a quotient, we can take the absolute value of each factor. So let's get x minus 9 to the absolute value by itself, so divide both sides by 5. So this simplifies to the absolute value of x minus 9 is less than whatever we get when we do 0.01 divided by 5. So 0.002. Notice this other statement says that the absolute value of x minus 9 is less than delta. So if the left sides match, then the right sides have to match. So that means delta is 0.002. So again, let's go back to what does that mean? So remember, this is the distance in the y direction. So if our distance in the y direction is 0.01, so if we arbitrarily pick a point that is 0.01 from the limit, either above or below it, so that distance is 0.01, or that distance is 0.01. If we are that close in the y direction, that corresponds to this distance in the x direction. So that means from here to here, or from here to here, those are 0.002. For a limit to exist, if we are getting closer in the y direction, we're also getting close in the x direction, and vice versa. If we are getting closer to c in the x direction, that has to correspond to getting closer to a particular value in the y direction. That's what a limit is. So if we can find this value, that shows that our limit exists. Now part B, we're just doing the same thing again. We just have a different epsilon. The difference in the y direction, that's referred to as our epsilon. Think about that in ordered pair, and x comes first, then a y. This is delta, that's epsilon. Delta alphabetically comes before epsilon. So delta refers to the distance in the x direction, epsilon refers to the distance in the y direction. Difference in x's, delta. Difference in y's, epsilon. So let's rework this whole thing. Put in our function, 5x plus 9, minus our limit, which was 54. That's this time going to be less than 0.005. Whenever x minus c, we're still approaching 9, whenever that's less than delta. So this time let's find delta that goes with this epsilon. So we're going to do the same thing. We're going to end up with 5x minus 45. So we're going to be able to factor out of 5 and get 5 absolute value of x minus 9 is less than 0.005. If we divide both sides by 5, we get the absolute value of x minus 9 is less than 0.001. Our other absolute value was x minus 9 is less than delta. So if we have an epsilon of 0.005, that corresponds to a delta of 0.001. Because if these match, then those match. So there's just a relationship here. If we're this close in the x direction, we're that close in the y direction, and vice versa. And I said that backwards. If we're this close in the x direction, that corresponds to this close in the y direction. On the previous one, we demonstrated a limit by expressing that if we get closer in the y direction, we simultaneously get closer in the x direction. And we did that for very specific distances. More generally speaking, and to do a more formal proof, we want to show that for all values of delta, if we are getting closer to a particular distance in the y direction, we're getting closer to a particular distance in the x direction. You might say, well, when is that not true? Occasionally, if we're getting closer, for example, if we're getting closer to this particular x value, but that is an asymptote, as this distance gets smaller in the x direction, then the distance between that particular value and where we're going isn't approaching any particular distance. It's just going towards infinity. So we need to show that if delta exists, so does epsilon. And that if one gets smaller, the other gets smaller. So how are we going to do that? So first of all, let's speculate what the limit is. For this one, if x is getting close to 4, then our function is getting close to 4 plus 3, or 7. So our limit is 7. So we need to show that as f of x minus L, as that approaches epsilon, then x minus c is approaching delta. So we replace our function with x plus 3, because that's our function. We replace L with 7. And over here, we replace c with the value we're approaching. We're approaching an x value of 4. So on the left, x plus 3 minus 7, that simplifies to x minus 4. Over here, x minus 4 is less than delta. So since these match, then those match. So that means epsilon and delta are equal. So whatever this distance is, this is the same amount. If we're 1/100th of a unit away from 4 in the x direction, then we would also be 1/100th away from the limit in the y direction. If we're 1,000th away from the x, or from 4 in the x direction, we would be 1,000th away from the limit 7 in the y direction. And notice, if this one gets smaller, this one gets smaller. If this one gets bigger, this one gets bigger. So as long as if one gets small, the other one is also getting small, then yes, that limit exists. So as we go on, this one doesn't ask us to do a proof. It just wants us to find the limit. And one thing they tell us is that when we have polynomials, we can find the limit by direct substitution. So replace x with 9. 9 times 9 is 81 minus 2, so we get 79. So that's our limit. We're not proving it, but even if we made a table and picked x values closer and closer to 9, we would get an answer closer and closer to 79. Same thing here. Even though this is not a polynomial, our function is not undefined at 2. We get an answer when we plug a 2 in. 2 plus 2 is 4. The square root of 4 is 2. So that's what we're approaching. If we pick values closer and closer to 2, we're going to get an answer that's closer and closer to 4. The exceptions to this is when the value we're approaching is a boundary value, meaning it's close to where we become undefined or where something ceases to exist. We're not dealing with that right now. We're dealing with polynomials or polynomials raised to powers. And there are some other examples as well. Even if we have a rational expression, if this particular number does not make this undefined, then we can find the limit by direct substitution. Replace x with 7, replace the other x with 7, so we get 6 times 7 on top. We get 7 plus 2, which is 9 on bottom, so we get 42 on top. The square root of 9 is 3. That reduces to let's see, 14. So that's our limit. As x gets closer to 7, we get 14. So that's nicer than having to plug in lots and lots of values to find out what we're going towards. Later we'll talk about continuity and discontinuity, and we'll look at times where direct substitution doesn't really give us the limit. But many types of functions we can just plug in, and that's what we get. What if our function, if when we plug our number in, we don't have a hole or we don't have an asymptote, then whatever we're approaching there, if there is a point here, then as we approach that from both sides, that y value is our limit. So that's what we've done on these last several. We've had functions that whatever x value we're approaching, whatever x value that we're approaching, either from the left or from the right, when we plug that value in, we get a point. It doesn't make it undefined. So as we're getting closer and closer to that in the x direction, then whatever that y value is, that's also our limit, because that's what we're going towards. We're going towards that particular y value. So on this one, if we substitute a pi in, we have a 9 out front, tangent of pi. If you don't know that off the top of your head, then you can take out your calculator and you can take tangent of pi, which is 0. 9 times 0 is 0, so that's our limit. Now what about this one? Now this one, if we directly substitute 4 in, we get 4 minus 4 on top, which is 0. 4 squared, well 4 squared is 16, minus 16, which is 0 on bottom, and that's indeterminate. Indeterminate. So what does that mean? So it is undefined, but often when things are indeterminate, the limit exists. We are going to be approaching something, but the question is, what are we approaching? So we could make a table. We could pick values closer and closer to 4. But in this section, instead of making a table, they want us to solve this algebraically. So this problem is found in 1.3. So how are we going to do that? Well, let's notice that this denominator factors. X minus 4, x plus 4. Also, let's note that for that function is undefined when x is 4 and when x is negative 4. That denominator was originally x squared minus 16. If we put a 4 in for x, we get 0 on bottom. If we put a negative 4 in for x, we get a 0 on bottom. So this particular function, I'm going to call it f of x. That has a domain of anything except those two numbers. Now notice that we have a common factor between top and bottom. So we can reduce that function. And when we reduce that function, we get this function. I'm going to call that one g of x. Now if we reduce, fractions that are reduced are equivalent to each other. If we compare 4 over 6 to 2 over 3, those look differently, but they're equivalent to each other, meaning they are of the same value. So if we reduce a function, these functions should be equivalent to each other. They should have the exact same value. The only difference is f of x is undefined at 4 and negative 4. G of x is only undefined at negative 4. Every other place, the functions have the same exact value. And we could test that. If we substituted, for example, 3 into the top function, we would get negative 1 on top, 9 minus 16 negative 7 on bottom, so 1, 7. If we substituted 3 into the bottom function, we would get 1 over 3 plus 4, which is 7. Same thing. And that's going to be true for any x that we plug in except the x's that are not in their domain. Let's just demonstrate by using one more point. We plug in 7, or let's say 8. 8, that's a little bit big to do off the top of our head, so let's pick something smaller. We plug a 6 in. For F, 6 minus 4 is 2. 6 squared is 36 minus 16, which is 20, so that reduces to 1 over 10. Well, if we get 1 over 6 plus 4, so we get the same thing. So these two functions are equivalent. They are of equal value everywhere except where they're. Now, for negative 4, they are both undefined at negative 4. But notice the top function is also undefined at positive 4. Is the bottom function undefined at positive 4? Well, no. So if we want to find out what is the limit as x approaches 4 of x minus 4 over x squared minus 16, since they share the same values everywhere except where they're undefined, then we should be able to compare that to this function and take the limit there. So this is F, this is G. So G, if we directly substitute a 4 in, we get 1 over 4 plus 4, which is 1 over 8. So for this function, by direct substitution, if x gets close to 4, our function gets close to 1 over 8. This function is still undefined when x is 4, but if we were to compare x values really, really close to 4, like 3.9, 3.99, 3.999, then the answer to that would be approaching 1 over 8. G is referred to as an extension of F. G is an extension of F. It's a comparable function that differs at a single point. So let's see. If we graph these two, at negative 4, both functions are undefined, so we actually have a vertical asymptote there. Now, when x is 4, G is 1/8, so that's that, and we're here. When x is 0, we're at 1/4, so we're here. If we pick negative values like negative 3, we would be at 1. So this function is doing like this. If we continue going to the left side, we would be doing like this. So this green, that's the function of G. Notice x cannot be negative 4. We are undefined at negative 4. We are defined at 4. At 4, we have a y value of 1/8. The only difference between G and F is that F does not exist when x is 4. Every other place, G and F have the exact same values. We demonstrated earlier that for other places, when we substitute the same value into G and F, we get the same answers. So their graphs are going to be exactly the same The graphs are going to be exactly the same with the exception of, at that point, f at x equal 4 does not exist. So for the function f, there's not a point there. There's just a hole. Well, if there's a hole there, all these points around it seem to be pointing towards where that hole is. So G and F are approaching the same point. G and F are approaching the same point. G actually gets there. F, there's a gap there. With F, we've got a little bitty part of our graph missing where x is 4. With G, we don't have a gap. We include that. But with F, we don't. But limits, remember, a limit is what we're going towards. So whether there's a point there or not, both functions are going to the same location. Hence, they're both going to 1 over 8. So the whole point here is if our function is indeterminate at the x value we're going towards, if we can find an equivalent function that is not indeterminate or not undefined at that point, they are going to have the same limit. They're going to go to the same value. Now, this doesn't go there. Let's cut that and move it over here. Let's do this one next. If we substitute a 2 in, we get 2 plus 7, that's 9. The square root of that is 3. So we get 0 on top and 0 on bottom. That's indeterminate. So on the last one we did, we demonstrated that if we get 0 over 0, then if we can find an equivalent function where we can plug a 2 in and get an answer, they are going to have the same limit. On the previous one, we were able to simply factor the denominator and reduce the fraction. Here we have to do something differently because we don't really have a good way of factoring this. So if we have one such that we have a square root in it and it's indeterminate, there's a little trick that we learned in algebra, and we didn't really use it that much. But it's for rationalizing denominators. And in the past, if we had a radical on bottom, for example, the square root of x plus 2, if we wanted to make this radical go away on bottom, if there are 2 terms, to make it go away, we would multiply top and bottom by the conjugate. And we'll see why in a minute. That's going to make the radical go away on bottom. We'll still have a radical on top, but that would get rid of the radical on bottom. We would actually end up with that. So we're going to use that trick to try to make this radical go away. So we're going to multiply the top by the radical x plus 7 plus 3, and the same thing on bottom. Now on bottom, I'm not going to distribute that. I'm going to leave it in factored form, meaning this factor times that factor. But on top, I am going to multiply it out and see what I get when I make my radical go away. So we have to distribute. We're going to do this radical times that radical. And anytime we multiply a radical times itself, anything times itself means we have that quantity squared. And if it's a square root squared, those cancel, leaving us what's underneath. So since these match, that means we have this radical squared, so we're going to get what's underneath. Then we're going to do that times 3, so we're going to end up with 3 of those square roots. We've got to distribute the minus 3, so we have minus 3 of those square roots, so those cancel, and then a minus 3 times a plus 3. And the bottom we're going to leave factored. So on top we have a plus 7 and a minus 9. 7 minus 9 makes a negative 2. So the top simplifies to x minus 2, and then we have an x minus 2 times that parenthesis. Now the good thing about this is that we have a common factor between top and bottom. That and that cancel. That's going to leave us a 1 on top, square root of x plus 7 plus 3 on bottom. So we made the radical go away on top, and look what went away on bottom, that x minus 2. That x minus 2 is what gave us the problem to begin with. X minus 2 has a root of 2, or a 0 of 2. 2 is what makes that 0, which makes our fraction undefined. It turns out that when we got rid of the radical on top, we also got rid of that x minus 2 factor, so this is no longer going to be 0 on bottom. The very piece that was 0 when x is 2 now is gone. So 2 plus 7, that's 9. So we have the square root of 9 plus 3. So 3 plus 3 is 6. So even though our original function is undefined when x is 2, we were able to do some algebra. We multiply top and bottom by the same thing, so all we're doing is multiplying by 1, so we're still equivalent. So this fraction is equivalent to the original one. The only difference is where we are undefined, our domain. So they are going to approach the same y value when x is 2. So this one approaches 1/6. Therefore, the limit to this one is going to be 1/6 when x approaches 2.